Hello, everyone. So we're going to work on chapter 7 in this video. Chapter 7 is about estimating confidence intervals. Remember in chapter 6, we defined unbiased estimators. We defined 3 of them, which are proportion, mean, and variance. So we're trying to estimate confidence intervals for those in this chapter. 7.1 is going to be for proportions. 7.2 is means. 7.3 is variance, but we're only going to cover section 7.1 and 7.2. So I wanted to show you some of these questions so you have an idea of what to do. So a critical value, Z alpha over 2, that's just a Z-score with an area of alpha over 2 to the right. So let's find this. Remember, the confidence level is 1 minus alpha. So we can solve for alpha here. That means that alpha is 0.11. We subtract 1 minus 0.89. 0.11, and then we divide by 2 because we want alpha over 2. So this should be 0.055. Now we want a Z-score with an area of that to the right. So there are 2 ways of doing this. We could either find this value in the body of the table, and that is going to give us a negative Z-score, and then we just make it positive. Or we could subtract this from 1 and then find that value in the body of the table, and that is going to be our critical value. Either way, the answer will be the same. So what I prefer to do is simply find this number and then make the corresponding Z-score positive afterwards. So let's go to our table A2. Look for the closest number to 0.055. It should be right here. I believe this is closest one. 0.559. No, 0.0548. So that is negative 1.60 even. And we have to make it positive. Remember, this will always be a positive number. So that is our final answer. Let's check. Fantastic. So we've been doing this like in chapter 6. They're asking us for a Z-score with an area of alpha over 2 to the right. Okay, let's try question 9. So here we have this confidence interval. It's an interval that starts at 0.222 and ends at 0.888. And we know that each one of these 2 values is of this form, p hat minus e and p hat plus e. So remember, p hat, that is the point estimate, that is the center of the interval. So it's the point that is right in the middle between our 2 limits. So that is how we find it. We find the midpoint between 222 and 888. So we add them and we divide by 2. (0.555). And then for the margin of error, there are actually 3 ways of doing this. Maybe there are more, but I'm going to tell you 3 ways of doing this. We want to find the distance between either one of these 2 limits to the middle. So that would be 888 minus 555, or 555 minus 222, Or we can also tell that between the lower limit and the upper limit, there are two margins of error. So we can calculate that difference first and then divide by 2. But anyway we do it, we would get 333. So p hat in this case is 0.555, and the margin of error E is 0.333. Now about question 10. We want to express this confidence interval in this form. So notice we're starting here, 0.041, and we are ending in 0.091. This question is very simple. Let's not overthink. Like maybe we think of this, we think, no, this is too simple, and then we try to do something else. Sometimes we should not overthink our answers. So that is all we do. So now let's do question 16. Now this is like more of a longer problem. Like let's try to do one where we do all the steps to find our confidence interval. So what does that entail? We need to find our point estimate p hat. We need to find our margin of error E. And for E, we will usually need a critical value. So let's do all that. Let's take a look at the problem. In a science fair project, Emily conducted an experiment in which she tested professional touch therapists to see if they could sense her energy field. She flipped a coin to select either her right hand or her left hand. And then she asked the therapist to identify the selected hand by placing their hand just under Emily's hand without seeing it and without touching it. Among 304 trials, the touch therapists were correct 140 times. Complete parts A through D below. Part A, given that Emily used a coin toss to select either her right hand or her left hand, what proportion of correct responses would be expected if the touch therapist made random guesses? So that should be 0.5, because it's either head or tails. Part B, using Emily's sample results, what is the best point estimate of the therapist's success rate? So remember, the best point estimate for a population proportion is the sample proportion. That means we calculate the proportion in the sample that we have. So how many successful therapists did we have in this experiment? 140. And how many attempts did we have total? 304. Remember, a proportion is a quotient. So sometimes we will be given this as a decimal or as a percentage. Some other times we will be given the integers and we have to calculate the quotient ourselves. So this is 0.461 rounded to 3 decimal places. Good. Using Emily's sample results, construct a 90% confidence interval estimate of the proportion of correct responses made by touch therapists. So we have the point estimate. Now we need to find the margin of error. So let's find that here in this little box right here. So we need a formula that would be Z times the square root of P times Q over N, if I'm not mistaken. We have it right here. Let's take a look just to make sure. Yes. So that's the formula we want to use. So let's start. So first we need our critical value, and that is with a confidence level of 90%. So remember, this is what we did for the first question in this video. We know that 0.9 is 1 minus alpha. So that means that alpha equals 0.1, and then we need alpha over 2. So that is 0.05. Now we'll look for this number in the body of table A2. 0.05, 0.05 here, 0.05, 1.645. So our Z-score is 1.645. Okay, so that is the first number we write here, 1.645 times the square root of p hat. P hat is the value we found, the sample proportion. 0.461. We multiplied that by q hat, which we know from chapter 5. Q is simply 1 minus p hat. So that is 0.539. And we divide by the sample size, which in this case is 304. So once we have identified all these values, we plug them in the formula. 0.461 times 0.539 over 304. We take the square root of that and we multiply that by the critical value. So this gives us a margin of error of 0.047. So we have p hat, we have the margin of error e. We know the lower limit is going to be p hat minus e. So that is 0.461 minus 0.047, which is 0.414. And the upper limit is going to be p hat plus e, which is 0.461 plus 0.047. 0.461 plus 0.047, 0.508. And that should be our confidence interval. And lastly, part D. What do the results suggest about the ability of touch therapists to select the correct hand by guessing energy fields? So notice that if we guessed someone who does not claim to be a touch therapist, we would expect 0.5. And the results show that that's where the touch therapist results are as well. So it's kind of like the same thing, right? So let's take a look at all the options. Option A, since the upper confidence limit is above 0.5, there appears to be evidence that touch therapists can select the correct hand by sensing energy fields. But we also have the lower limit being below 0.5. Maybe not option A. Since the confidence interval is not entirely below 0.5, there appears to be evidence that touch therapists can select the correct hand by sensing energy fields. Again, this first part is true, but this is not the right conclusion for that. Option C, since the confidence interval is not entirely above 0.5, there does not appear to be sufficient evidence that touch therapists can select the correct hand by sensing energy fields. Sounds good. Or option D, since the lower confidence limit is below 0.5, there does not appear to be sufficient evidence that the touch therapist can select the correct hand by sensing energy fields. So notice the difference between C and D. C is talking about the interval itself. So the upper limit of that interval is not completely below it. So there is not sufficient evidence. What D is saying is only comparing the lower limit. So if the lower limit is below 0.5, it's kind of like the same as if the upper limit is above 0.5. Like it doesn't really tell us anything. Okay, so I think this is it for section 7.1 part 1. Like basically question 16 is what we want to do in this section. We want to find the confidence interval for a proportion. So let's move on to 7.1 part 2, which is kind of like the same topics. But very specifically, we want to find sample sizes for these types of experiments. So let's do question 3 in assignment 7.1 part 2. You are the operations manager for an airline and you are considering a higher fare level for passengers in aisle seats. How many randomly selected air passengers must you survey? Assume that you want to be 99% confident that the sample percentage is within 4.5 percentage points of the true population percentage. Complete parts A and B below. Part A, assume that nothing is known about the percentage of passengers who prefer aisle seats. Now, this is relevant because we have two different formulas for the sample size. We basically have one, which is this. But notice that for this formula, we need a p hat and a q hat. That means we need some estimate about the sample proportion. But for a sample proportion, we need a sample. And for a sample, we need a sample size, which is what we're trying to find. So sometimes we might not know what these two values are. In that case, we take p hat and q hat to be 0.5. Okay? So that is the case we have in question 3, part A. We don't know what p hat or q hat are. So we take both of them to be 0.5. So we multiply 0.5 times 0.5 here. We multiply by the square of the corresponding critical value and divide by the square of the margin of error. So let's do that. Here, we want to first find the critical value, square it, multiply by 0.25, because that is p hat times q hat, 0.5 times 0.5 equals 0.25, and divide by the square of the margin of error. So we need to find the corresponding critical value for 99%. Remember, we have those on our table. We can find them like we find the values in the last example, but we can also go to this bottom right corner where we have some common critical values. So for a confidence level of 90, which is what we have here, no, 99, the corresponding critical value in a normal distribution is 2.575. So 2.575 squared times 0.25 over the square of the margin of error, which we're told is 4.5 percentage points. So let's plug this in and see what we get. I just noticed this is a percentage. We need to divide by 100. So let's do this one more time. So we get 818.595, etc. And remember, this is like an exception. Whenever we are calculating a sample size, we are always rounding up. So the answer should be 890. Good job. Now for part B, assume that a prior survey suggests that about 35% of air passengers prefer an aisle seat. So this is the same formula. We want the z-score squared times p hat times q hat over the margin of error squared. But now we do have a value for p hat and q hat. So our critical value remains 2.575, right? 575, yes. We multiply now by p hat, which is 0.35, and q hat, which is 0.65. and then divide by the margin of error squared. So let's find this. We should get 744.92, but we still want to round up. And remember, these are always integers, right? Because we want a sample size. We want to know how many subjects we need in an experiment or a survey. And if we forget, we're all told round to the up to the nearest integer. So this is just for this formula we're using for n. But this is a good example because it shows the two cases. Whenever we have an estimate for p hat and whenever we don't. So that's parts A and B. Okay. And that's it. That's 7.1. And I also want to show you 7.2, which is the same idea. But now instead of doing a confidence interval for a proportion, we're doing a confidence interval for the mean of a population. And there is one thing that changes. Whenever we're working with a mean, we are not going to use the normal distribution table. We're going to use the t-student distribution table. So that is a different distribution, which I must have here somewhere. It's going to look like this. The shape is bell-shaped as well, like a normal distribution, but the values differ, okay? And to calculate the areas on that, we will be using table A3. You can find this in the notes for chapter 7, right here. And yeah, you need to know two things. You need to know the area in one tail or in two tails, and you also need to know this new concept we're defining, which is degrees of freedom. And to know the degrees of freedom, we will simply take the sample size and subtract them. And that's it. Then we will know what row to use. If we have a certain degree of freedom that is not on the table, like if we had 47, what we do is we use the one that is closest to it. Okay. So let's start with question 3. And this is just finding a critical value, but now in table A3. So the critical value T of alpha over 2, that corresponds to a blank % confidence level with 1,000 degrees of freedom is 2.33. So let's go to our table. We know we have 1,000 degrees of freedom. So we know we want to look at this row. Let's try to find that value here. So our value is 2.33. We can see this in this column. So this column is column for 0.02. And remember that 0.02 is 1 minus alpha. So the confidence level is 1 minus 0.02, which is 0.98. And that 0.98 as a decimal is multiplied by 100 so that it becomes a percentage. Okay, so let's do this again really quickly, just to summarize it. We look for this row in table A3. We identify the value, 2.33, and we identify what column it's in. So we go to row 1000. We find 2.33. It's in the column of 0.02, and then subtract that from 1. And we get it. So that's how we use the table. Let's do question 6. This is finding on well, let's see what they ask us to find. Here are summary statistics for randomly selected weights of newborn girls. N equals 36, X bar equals 3,197.2 grams. The standard deviation is 692.6 grams. Use a confidence level of 95% to complete parts A through D below. So first we identify the critical value. So we know N equals 36. We go to that row on our table right here. We know our confidence level is 95%. So that means that alpha is 0.05. So 0.05 is here. The middle column for 36 is 2.028. Oops. Okay. Yes. Remember, this still happens to me. It might happen to you too. Always read how many decimals you want in your final answer. So that's how we find the critical value. We have to round properly. We get the result we want. Now, how do we find the margin of error? Well, let me show you. It's a similar formula, but it is a little different. The margin of error is now this. So we have this critical value. We multiply by the standard deviation and divide by the square root of the sample size. So that is T times S over the square root of the sample size. So we know the critical value. We found that on part A. We multiply by the standard deviation, which is 692.6. And then divide by the square root of the sample size, which is 36. So that is 2.03 times 692.6 divided by 6. 234.3. Let's check if this is correct. Nice work. And now we need to find the confidence interval. So it's the same idea. Point estimate minus the margin of error, that is the lower limit, and point estimate plus margin of error, that is the upper limit. So now the point estimate is the sample mean, which in this case is 3,197.2. We subtract the margin of error we found of 234.3. We get 2,962.9. And we do the same for the upper limit. We take the point estimate, which is the sample mean, 3,197.2, plus the margin of error, which we found to be 234.3. $3,431.5. Perfect. And for the write a brief statement that interprets the confidence interval. So we always have some different options for this. There is one way to interpret this result, which is this. We are confidence level confident that the interval actually does contain the true value of mean. So let's try to find the one that resembles that the most. One has 95% confidence that the sample mean weight of, let's take a look, there is 95% chance. So it's not chance, so not A, one has 95% confidence that the interval from the lower bound to the upper bound contains the true value of the population mean weight of newborn girls. So this one's tricky. All of these seem to say the same thing, but they don't. If you struggle to understand what the right answer is, you can go back to the notes, and that is basically the literal phrase we want to use. Okay. And just as in section 7.1, we can also find sample sizes in section 7.2. The formula is going to be similar, but it's not going to be the same. So this is the formula for a sample size in a mean confidence interval. So it's the critical value times the standard deviation over the margin of error, and then we square that. Okay, notice that we are using a normal distribution here. Let's take a look at question 11. The ages of a group of 155 randomly selected adult females have a standard deviation of 16.6 years. Assume that the ages of female statistics students have less variation than ages of females in the general population. So let sigma equals 16.6 years for the sample size calculation. How many female statistics students' ages must be obtained in order to estimate the mean age of all female statistics students? Assume that we want 99% confidence that the sample mean is within 1/2 year of the population mean. Does it seem reasonable to assume that the ages of female statistics students have less variation than ages of females in the general population? So how do we find the sample size? Well, we use our formula. We know that n equals the square of our critical value times the standard deviation over the margin of error. So that is our critical value for a 99% confidence interval. We can use this bottom right legend here. For 99%, we want 2.575. Multiply that by the standard deviation, 16.6, and divide by the margin of error, which is 1/2 year of the population. 1/2 year, it's half. So we calculate this, 2.575 times 16.6, 0.5 squared. And remember, we always round up the nearest whole number as needed. So this is 7,309. Perfect. Does it seem reasonable to assume that the ages of female statistics students have less variation than ages of females in the general population? You would think so. Usually students are like in a more narrow age range. Yes, because the statistics students are typically younger than the population in the general population. That might be the case. Yes, they're like during school. Most students, but that's not the rule. Okay, so that's it. That's all the examples I wanted to show you. I hope this is clear. If you have any questions, please let me know. You can write me an email, or you can also join SI sessions or schedule one-on-one tutoring, and we'll be happy to help you. Have a good one. Stop share.